Since in this course we will be mostly following a historical development of nuclear and particle physics, I thought that I would start with a historical context in which the discoveries of nuclear and particle physics came from. And so much of modern physics comes from discoveries made in the 1890s. The discovery of X-rays by Röntgen in 1895, picture there of his wife's hand taken in X-rays. In 1896, Becquerel discovered radioactivity, and also work of Marie and Pierre Curie at that time. Here's Becquerel's photographic plate imaged by the radioactive sources. And in 1897, J.J. Thomson demonstrated that cathode rays were actually particles, the electron. Here's a picture of his apparatus. So what was the view of a physicist at the end of the 19th century? They would have been well conversed in Newtonian mechanics, including Lagrangian formulation, which came from 1788, and Hamilton's formulation in 1833. I emphasize those because of, they emphasize conservation of various things, in particular energy and momentum and angular momentum, as the things that are important in Newtonian mechanics. Electrodynamics had just been finished with Maxwell publishing his results in 1865. Should note that the four Maxwell equations you're used to are due to Heaviside, but that had also been done. And importantly for atoms, statistical mechanics had been developed by Boltzmann, finishing in around 1870. Gibbs made some contributions later, and so this was quite just before this time of the 1890s. Should point out that not all physicists believed in the atomic theory of matter. The most notable skeptic of the atomic theory was Mach, who said there just wasn't enough physical evidence that you couldn't see an atom, and so how did you know? Atoms were mostly a concept used in chemistry, with Dalton at the beginning of the 19th century publishing his law of multiple proportions and how chemical processes seem to take proportions that are low integer values, rational values of each other. And Avogadro in 1811, found that gases had the same number of molecules at the same temperature and pressure and volume. And so one could also attribute that to atoms. One reason you might not believe in atoms is some other, model of materials that were put forward. Phlogiston, to talk about fire and what happens. Caloric as, heat transfer. There's thought to have to be a substance for that. And of course the luminiferous ether, which was still in vogue in 1890 as a model for what carried the electromagnetic waves. There was some evidence even to the contrary for the atomic model, which was that ionic solids didn't always combine in a 1-to-1 ratio or a low ratio of integers. Sodium and chlorine don't combine 1-to-1 exactly to make salt because of defects in the lattice, as it turns out. So I should also point out that much of the progress in modern physics that happened in the 1890s happened because of the improvement in vacuum technology. The medievalists didn't believe in vacuum at all, of course, but in the 17th century, Torricelli invented the barometer, and so if you put mercury in a tube and tip it over, a vacuum forms at the end, and here's a picture of Torricelli's vacuum. And the vacuum there was about 10 torr, or about 1% of an atmosphere. And in the next 200 years, this barely improved one order of magnitude. In the Great Exhibition, there was a vacuum, and it had a pressure of about 0.1% of an atmosphere. But then in the second half of the 19th century, there was a lot of improvement, both in the Crookes tube and in Edison. So by the 1870s, you were getting down to 1/millionth of an atmosphere as the best vacuums that could be achieved. And that was because you had better seals on your vacuum chambers, you outgassed the materials, and you used diffusion pumps. Diffusion pumps use statistical mechanics principles to say why you can you can get more stuff out of the vacuum. That allowed spectroscopy. You didn't need the best vacuum for that, but for discharge tubes, you only have about 10 to the minus 3 atmosphere with kilovolts, and the light comes from all parts of the tube because the electrons, as it turns out, are bouncing around in the gas that's remaining. But Crookes tube got to a pressure of 10 to the minus 6 atmosphere, and if you put 10 kilovolts on the cathode rays that develop, they can go through the atmosphere and not hit any atmosphere molecules for tens of centimeters, and that's what you really need to study cathode rays and therefore the electron. So those discoveries, a few more words about them in the 1890s. Röntgen discovered X-rays on the 8th of November in 1895 using an apparatus that looks something like this here. What you have is a cathode and an anode, and you put a large voltage, and if there isn't any gas in the middle to scatter the cathode rays, the electrons, they come and hit the anode very hard, and they produce penetrating radiation, and that's what the X-rays are. J.J. Thomson discovered the electron in 1897 using an apparatus that looks like this. Here's the cathode and the anode, and if the cathode rays come out, the electrons, as they turn out to be, they're accelerated toward the anode, but they might miss. If there's a slit in the anode, they can come through and travel free through this evacuated glass tube. The vacuum's so low that they just go without hitting anything. Or maybe there's just enough to make them be seen as they go through. A few of them hit. What J.J. Thomson did is he took an electric field, shown here by these capacitor plates, and a magnetic field given by the magnets here, and by crossing them, you can measure the mass, or the velocity, actually, of the charged particle that goes through. First of all, they are charged because they deflected in magnetic and electric fields, but you can also adjust it so that the magnetic and electric field effects cancel, and therefore measure the mass of what would be the electron, and you find, and Thomson found, that it was much lighter than what they knew the hydrogen atom to weigh. That's the first fundamental particle, which simultaneously established atoms at some level and started subatomic physics, because the electron is a part of the atom. Finally, radioactivity was discovered in 1896 by Becquerel and the Curies. It produces penetrating radiation directly from matter. The matter is just sitting there. And it was found that the rates of this radioactivity change. Radioactive materials have a half-life. That meant that the matter could change. It's not immutable, which was kind of a challenge to the atomic theory, since the atoms are not, things that stay forever now. But you could also produce new elements like radium and polonium that the Curies found. It's important that the penetrating radiation, we're going to use them a lot later, they come in 3 kinds that were identified very quickly: alpha, beta, and gamma radiation. If you put your radioactive source in lead, and then leave a gap, and then see what comes out, put a magnetic field on it, the alpha radiation bends one way, the beta radiation bends the other way, so they have opposite charges. The beta radiation bends a lot more, so it's lighter. And the third kind, gamma radiation, doesn't bend, and so it is neutral.